Well, so that's a pressure, right? The last talk of the whole summer school. But well, thanks for the invitation. And then I thought, because you now have heard about the like what neural machine translation is, what deep learning is, and then all the other things that are necessary to know about how to apply the machine learning techniques to natural language processing. So I thought I'm going to show you what the latest directions in neural machine translation are. And then when I say latest, that's like the really latest as in like the past few weeks kind of thing. So let's go over the brief history first. I just cannot give you the comprehensive history, but you can find Andy Wei somewhere in the audience who can tell you all about the machine translation starting from like 50s. And then nowadays he's actually reading the deep learning book, so he probably can tell you about neural translation as well. So if you go into the history of the machine translation, in fact, funny thing you notice is that the neural machine translation, which is a subset of the statistical MT, started slightly earlier than IBM models, which were the world level, let's say, translation system, and then about 15 years earlier than the statistical phrase-based machine translation system. Well, meanwhile, the rule-based system has been going strong, and then it's still being largely used in the industry. So what do I mean by neural MT actually started very, very early? In 1987, Bob Allen, back then at Stanford, he's now a professor at Yonsei University in Korea. He wrote a paper at the very first international conference on neural net, writing about how to build a neural net that can do the translation. He used, let's say, about 3,000 sentence pairs to train a model, and then tested on the 33 sentences, and it's clear why it didn't really work, right? He used 3,000 sentence pairs as a training set. And then after about 5 years, Chrisman, back then at CMU, he wrote another paper that was extending a model called the RAM back then to build a neural net that's going to do the translation. And again, he used the English-Spanish sentence pairs in order to train this model, and then show that among the 50 sentences that he used for testing, 75% of sentences were correctly translated. But of course, this whole thing kind of stopped. Although it kind of stopped, everyone kind of knew that, okay, maybe the neural nets are the right way to go. In fact, this is a kind of, let's say, unfortunate book that was written and published by the Hutchinson and Somers in 1992. And then it didn't talk anything about the statistical MT system, which was like proposed a year or two earlier. And then it was, let's say, swamping the whole translation, let's say, landscape. In their book, they said that the connectionist model, you can just view it as a neural nets, to natural language processing is clear enough, and it's the most psychologically real model of how humans understand and communicate. Whenever I quote this, people go crazy and then either praise my finding of this phrase, or kind of, let's say, go crazy and starts bashing Hutchinson and Somers. But we'll see how you guys feel. But then the whole neural net-based machine translation kind of died off. Nobody really cared until 1997. Not far from here in Spain, two groups, one from Forcada and Necos in Alicante, and then from the Castaño and Casacuberta from the Valencia, they reproposed to use the neural net to do the translation directly. And then if you look at this figure, you probably find it very similar to all the models that Chris Dyer talked about this morning. That's precise the network. They had the encoder, which is a recurrent neural net that's going to read the source sentence. And then based on what the encoder has encoded, the decoder, which is yet another recurrent neural net, is going to generate one word at a time, the translation. So, well, that was 1997. Of course, again, nobody was actually following up on that work. Even Mikhail Forcada himself kind of gave up on working on this direction. And then in 2000, as you already learned during the summer school, the neural language model was proposed. And then the Holger Schwenk from France started to use it for everything he could, let's say, find. So he started with the automated speech recognition, where language model is super important. He plugged in the neural language model, and then he showed that you can get better. And then, of course, on the machine translation system, as the kind of filtering stage at the end, he used a neural language model to get some improvements. But this is slightly less interesting because we had to have an existing system there, and then the neural language model was only used to filter out the irrelevant translations or the transcriptions as well. And then around 2014 and 13, people started to notice that, in fact, we can actually do the tighter integration between the existing MT system and a neural net translation model by including the neural net translation model as one of the scores you use for building a log linear model. Did anybody actually talk about the statistical MT during the summer school this year? Zero. No one talked about it. Okay. But there is something like that, like that people used to use, a long time ago, yes. But anyway, and then around, right after this, people, including myself, we got much bolder and then decided to, okay, can we actually replace the whole thing with the neural net and then revisit the whole premise from the 1997 and 1987. And then that's what, kind of started the whole wave of the neural machine translation systems. And then already in 2015, we noticed that the 1 year of extensive research by folks from University of Montreal, including myself, and folks from the Edinburgh. You probably heard the lecture from the Lexi Birch earlier. And then we noticed that, in fact, now with the amazing computational resource as well as the advances we have made on the deep learning or the artificial neural net, we can actually go beyond what we thought were the best system back then. This is in the case of the English-German system. Back then, the best system was the syntax-based, phrase-based machine translation system, and then within 1 year, neural translation system was doing better. Of course, these scores, the blue scores, are a bit artificial in the sense that, okay, does it actually correspond with the human evaluation? That's kind of two different stories, but I'll just assume for today that the blue score is the absolute metric that we're going to use. And then this year, WMT, at the workshop on statistical machine translation, well, they changed the name, so it's the WMT, but the conference on statistical machine translation, they had the news translation shared tasks. And then for all these language pairs, except for going from Finnish to English, well, Finnish is a kind of weird language, so I think we can kind of safely ignore it, except for the specific language pair direction. Is there anybody from Finland, though? I lived there 5 years. I think I'm qualified to say that, all right? Except for the specific language pair direction, for all the other language pair, we noticed that the neural MT system actually now have become the state-of-the-art system. So this is great. So are we all done? Should we go home and then, like maybe I should have patented it and become billionaire together with Yashua and Dima, but we didn't do that. And the reason why we didn't do that is that, first of all, we are very against patents. But the most important thing is that building a single pair, a better or the best single pair translation system has never been our goal from the very beginning. What we wanted to do was we wanted to use the neural net to do something beyond building a single pair, single direction machine translation system. And then I'm going to tell you about what are those things. So first, let's think about the multilingual translation. So what is the most, let's say, important characteristics of the neural machine translation system or any kind of neural net is that you're going to always project some kind of input into the continuous vector space, and then all the manipulation happens within the continuous vector space until we decode out the discrete symbols into the output space. What it means is that once we project everything into the continuous vector space, we can do whatever we want. And then the nice thing about the continuous vector space with all those differentiable encoding and decoder is that we can backpropagate the error and then assign the correct credit to every single component of the whole system. You probably heard about the backpropagation throughout the summer school. And then what it means is that, okay, all we need to do is project all those different sentences or the symbols in different languages into a single shared common space and then try to decode it from there. So in fact, a lot of people have noticed it quite some time ago, already starting from the 2011-12, and you can actually go all the way back into the early 2000s when the neural language model was proposed. And then when we did the visualization of the actually trained model, we could see that, okay, so this continuous vector, so this is the visualization of the vector you get from the encoding recurrent neural net for different sentences. Of course, it's been projected down into a two-dimensional space using PCA. And then when you looked at all these sentences, people noticed that, actually, they do reflect, or the distances or the similarities in this continuous space do reflect the similarities, however that is defined, in the original input space. And then although I'm showing only the 2 dimensions, 2 principal directions, we notice, a lot of people have noticed in various papers that in fact these vectors, which is very high dimensional, can encode multiple dimensions or the degrees of the similarities. So that's all good. Then obvious question is, can we actually do something like this? Can we build some kind of encoder that's going to take as an input a sentence written in any of these languages and then project it into some kind of universal or common shared sentence space that is continuous, and then build a decoder that can decode out from any of these vectors into the translation. Once we do that, we effectively get a multilingual translation system that can use for any of the language pairs that you can think of. And the interesting thing is that this part is going to be largely stripped of the hard linguistic symbols. So there's a big question of, can we actually do that? So in 2015, early 2015, Orhan Firad and I decided that, okay, let's try it out. I don't think we can ever prove that whether it's possible or not. So we're going to build it and then see what happens. So we decided that, okay, we're going to build a single machine translation system that's going to take as input a sentence written in any of these 6 languages, and then translate it or decode it out into any of the 6 languages again. So what are the design choices we made? The first one we made was that, okay, we're going to have one encoder, one encoding recurrent neural net per language, per source language, so that if the source sentence is going to be given in German, then we're going to use the German encoder. And then for target language as well, we're going to build one decoder, so one decoding recurrent neural net per target language. So if you want to translate whatever has been encoded into this language agnostic continuous vector space, we're going to choose one of the target language, use that decoder to generate the translation. But at the same time, we wanted to ensure that we can actually share the knowledge across all those different language pairs. So we decided that we are going to use the attention mechanism, which we will learn this morning, and then share that for every language pair directions you can think of. And at the same time, like one thing is that, okay, you can always build this kind of neural net if you have the full observation, right? So if I have a multi-way parallel corpus, just such as a Europol, I can just train it in a trivial way, just finding all those, let's say the correspondence across the languages. But what we don't want is precisely that. What we want is that we want to be able to use all the resources we have. So we're going to train this model using only the bilingual parallel corpora. Now, how are we going to build this? It looks a bit complicated, and then in the figure, it looks even more complicated. So this part is the encoder. This part is the decoder. This is the shared attention mechanism part. But like throughout your labs, I'm pretty sure you have learned that it's all about let's say, playing with Lego, right? So it's the neural net, and then you have the parameterized functions here and there. Now, it's all about how you're going to plug something with another and making sure that the information is going to flow from the input to the output, and then now you can train it. So I'm not going to go into the detail. You can read our paper from last year's NACO. And then we built this model, and then we had to ask ourselves before running all those experiments, okay, what are the things that we expect? So if the goal was not to build a single pair language translation system, but to build a multilingual system, why do we actually want to do that? So there were a few, let's say, conjectures that we made, or the hypothesis that we made. The first one is that we hope to see some kind of positive language transfer. So some languages are more difficult to learn. Some languages have less resources. Some languages have more resources. And there are a lot of different properties across the different languages. And then can we actually get that kind of transfer so that those language pairs that we know are difficult, can we do it better by actually borrowing the knowledge from those, let's say, language pairs that we know better? And then by doing so, can we get a better performance on the low resource language pairs? And then the reason why we came up with this hypothesis is that in our mind, let's say, sharing this attention mechanism puts a very nice structural constraint on the continuous vector space. So given a single language pair, the continuous space can be anything. But now, by having multiple language pairs, and then this continuous space has more constraints to satisfy. So this continuous space needs to work with English. This continuous space needs to work with German, French, Finnish, Czech. And then now we have more structure we have imposed more structure onto the continuous vector space. And then, of course, there's the effect of the regularization because the number of parameters grows linearly with respect to the number of language pair directions, unlike building all possible, let's say, quadratic number of models. Just the number of the parameters is much smaller given the same amount of data. And then in the next slide, I'm going to show you the result from another group's paper, which is from Google, is that once you train this kind of model, you can now try to visualize the continuous vector space or the sentence space so that vectors are going to correspond to the words in the sentence, and then now you can look at the trajectory. So for instance, here, these, let's say, yellow dots corresponds to English words or the word pieces that has been encoded by the encoder. And then now you can put in the sentences written in different languages through this network and then visualize this shared common continuous vector space. And then what they noticed was that this is the work by the Melvin Johnson at the Google Translate. What they noticed was that regardless of which language the source sentence was written in, if those sentences represent the same meaning or the same thing, then they're going to be clustered in the similar, let's say, one small, let's say, region of the continuous vector space. And then when you look inside, you see that they all move quite similarly. However, this continuous vector space still preserves the language-related information. And of course, like at this point, you should have noticed that and then, like not only at this point, but throughout the whole summer school, except for I heard that the Yoav Goldberg's, Yoav's lecture, you notice that when people talk about how to use deep learning for doing, like working with the natural languages, there's absolutely no mention of the languages when anybody describes a model. So when I describe about the multilingual neural translation system here, although I said, let's say English, German, Finnish, but even if I replace the English with, I don't know, whatever you want, image, video, like let's say what can be there, let's say handwritten, let's say OCR kind of thing, there's absolutely no change in how each of these network is built. What it means is that, in fact, a lot of things that you have learned in the context of the language processing doesn't really have anything to do with language itself. So I know that all of you are not really interested in or find this kind of image caption generation cool anymore, from this morning, right? Chris wanted to tell you about the image caption generation. You all said no, like that's so boring. But back in 2015, it was kind of, let's say, cool stuff. So what we did was that we keep everything as it is. We just replace the encoder with the convolutional neural net that's going to take as the input an image instead of a sentence. And then we could train the same thing with the same optimization algorithm. Really, like, we didn't change anything. In fact, I coded this whole thing up from scratch, and then there was absolutely no difference between the translation system and the image caption generation system. Now, what does it say? So looking at this image caption generation system and the multilingual translation system, the obvious or the natural next step is to go beyond languages and then trying to do the multimodal translation. When people actually do the translation, what we do is not only to look at the sentence alone, but we do look at a much larger context, or we do take into consideration much larger context. So where did that sentence actually appear? When the person was writing that sentence, what was the situation? If it was a conversation, then what were the previous utterances so that I can know better about what each of the word means? So recently, from last year, the Conference on Statistical Machine Translation introduced a new track called multimodal translation. And then people have just barely started working on it, but already are showing some positive results. So in this case, now I have one language and one image. So, and the image can be considered as yet another language. And now you do the multi-source translation. And then by looking at both the actual sentence and then the context in which the sentence was written, so image caption is written while the person is looking at an image, you can do a better job of doing the translation. So this is the kind of first direction toward going beyond the usual sense of the single pair machine translation, in the sense that now we are ready to build a multilingual and multimodal neural machine translation system. And then there is a big, let's say, promise of doing translation or making the machine translation system closer to the human translation by reducing the gap or bridging the gap between how much, let's say, context each of the system has access to. So the next direction. So this is actually interesting, let's say, question that we all talked about when we started working on machine translation in Montreal. So how should we represent a sentence? Initially, when I went to Montreal in 2013 as a postdoc, I never really worked with the language before. So what I thought, because my background is computer science from the beginning to the end, what I thought was that, okay, of course, sentence is a sequence of Unicode symbols, right? That's a sentence, right? But then, Holger Schwenk told me that, no, sentence is a sequence of words. And then some people told me, no, words are too, like the too raw, you should go into the phrases. And some people told me, no, of course it's characters. And then, of course, my Chinese colleagues told me that, it's all pixels, right? Well, strokes are kind of difficult to get, so pixels are a bit easier. So this was actually a big question, and then, we didn't really have a precise answer to. And then, I don't think we still have a precise answer to. But at least from a neural net point of view, a sentence or the input is very obviously simply a sequence of vectors. And then those vectors are super dumb in the sense that we use so-called one-hot vectors, which is a vector that consists of all zeros except for the single element whose index corresponds to the word's index is set to 1. So what it means is that the neural net is really agnostic to what words are or what the sentence is. So what is the interesting property of this representation, one-hot representation, is that every single vector is equidistant away from each other. So there is no such thing as, okay, cat is closer to dog than the cat is closer to the. So we don't really encode anything. So it's like the most priorless encoding you could think of. And then the sequence of these one-hot vectors is the one that is being fed to the neural net. What does that mean? It means that, in fact, from neural net's point of view, it doesn't matter whether a sentence is a sequence of words, sequence of characters, sequence of, let's say, pixels, or the sequence of the Unicodes. It doesn't really matter. Neural nets just see these one-hot vectors and then trying to do its job of doing the translation. And then I started thinking about, okay, so then why don't we want to work with words? It may not be obvious. It may be obvious depending on what your mother tongue is. It's usually like that. So first thing is that it's really inefficient if you represent a sentence as a sequence of words to handle various morphological variants. Often we have a very suboptimal segmentation or tokenization algorithms. And then I don't know if you have been following some of the discussions in Twitter about all those differences, that subtle differences in the tokenization function in NLTK versus, let's say, Philip Cohen's sophisticated per code and so on, right? So it's all very suboptimal. And then we use independent vectors for all possible morphological variants when you don't really have to do so. And then there is the issue of lack of generalization to novel or rare morphological variants. I don't really speak Arabic, but my colleague who speaks Arabic told me about this token. I don't even know how to pronounce it, probably from right to left. And this token corresponds to and to his vehicle. And then that's novel thing. So we couldn't find that token in our training set, but that is a very natural token that you can use in the usual sentence. That's true, is it? Yes. Okay, perfect. Yes, so that's good, okay. And then we often use a single vector for every possible compound words as well. So this is going to be komi vaye kilowatt ditun is going to be 3,000 kilowatt per meter. No, hour meter. No, yeah, something like this. So that's one word, one token in Finnish. But now the very first one is going to be the root form is golme, which is 3, and then this is just one word. And then we assign the same number of parameters to these two words that have a very different amount of information. So that's very inefficient. And then there are some issues with the spelling. If you check the Twitter or the Facebook, is full of misspelled and non-trivial, let's say, novel words that people generate. And then if you go into the historical documents, surprisingly, the normal way of spelling anything is a very recent thing. If you go into the historical documents, some of the authors just want it to be very peculiar and then use a different spellings for the same word in a single document. You actually notice that quite a lot. And furthermore, if you want to build a translation system that's going to work for, I don't know, hundreds of languages, Now you somehow need to come up with a good segmentation and tokenization scheme for each and every one of them, and then it's often very difficult. So it seems like, okay, words don't look like the unit that we want to work with, and especially with a neural net which doesn't really care. So what should we do? Let's look at all those different ways to represent a sentence. So this is a Korean sentence that says the cat is lying on the bed. All right, so word level representation is going to be, you just segment it based on the blank spaces and then represent it as the first word, second word, third word, and fourth word. And then, of course, you can always do the morpheme segmentation or some kind of subword level you get the subword level representation, and then you get some kind of, let's say, at least statistically meaningful subsets, right? Subwords representation. Obviously, you can go into the kind of hybrid form where we're going to use a word level modeling, but each of the token is going to be represented as a sequence of characters or these something, right? So this is not precisely characters, but that's the kind of thing about the Korean. Or you can go for the fully character level modeling. You're going to just split everything into the characters and then consider everything as the token that needs to be read and generated by a neural net. And then more recently, people have realized that especially for the Chinese, Japanese, and Korean CJK languages, this is not really ideal either. And then even the Unicode is not ideal because Unicode was built by those Western people who don't understand these sophisticated letters, right? So for instance, the Graham Newbeck, who gave a talk yesterday, had a paper on how to model each of the character as a pixelated image. And then especially in the case of Chinese, it actually works amazingly well. So we decided that, okay, so what is the minimalistic we can go? So this is the minimalistic we can usually go. So the pixelating the thing is nice, but it's kind of expensive because you need to run the convolution on neural net for every character as well. So we decided that, okay, we'll go for the fully character level modeling. And then I was talking with a lot of other people on this, and then people were pretty skeptical about it, first of all. And then the second thing is that nobody has tried it. So Graham Newbeck tried it with a phrase-based statistical machine translation system like in 2007 or 8. It didn't really work well because of the inability or the data sparsity issue arising from the long-term dependencies that you need to model. But again, with the neural net, you don't really have that issue, especially with the recurrent neural net that you learned this morning. So we decided that, okay, let's try this. Why not? So first thing we tried was that there are two questions here. First, do we actually have to go for the fully character level modeling, both source and target side? Maybe not. And then we'll go for the target side, character level modeling only. And then there comes the question of, okay, can this attention mechanism, which a lot of people view as an alignment between the source and target symbols, can this attention mechanism work with the different levels of granularity in the source and target? If you view it as just a word level, let's say if you view it as a word level alignment, then it shouldn't work. So we thought, okay, let's try. And then it turned out that it just works. So we used the subword level representation based on the byte pair encoding, which I believe the Lexi told you about earlier. And the target was the character level representation. It was just a sequence of all the characters. Blank space is one character, Z here is one character, W is just one character. And then this is a visualization of attention mechanism. And then even though the granularity of the symbols or the segmentation on the source and the target side is completely different, the attention mechanism was able to find the correspondence. And then again, why is that possible? Because what neural net does is to project the whole thing into the continuous vector space. And then as soon as you can project it into the common continuous vector space, the attention mechanism, all it needs to do is manipulate the continuous vectors without having to be constrained by the hard linguistic symbols. And then we clearly see that it works really well. And then in this paper, we found that, okay, it actually works for the 5 language pairs that we tried. And then, of course, what would be the next step? We just go fully character level, right? Forget about any of the word or the segmentation. We're going to just consider the sentence as a sequence of symbols or the characters. And then, let the neural net look at the sequence and then generate a sequence of target characters. So, of course, there is a big issue is that the efficiency is a big issue because the attention mechanism that you learned this morning is the computational complexity is quadratic with respect to the length of the source and target. And that can be really large, especially if you start, let's say, representing the source and the target sentence as a sequence of characters. It can be like 100, 200, 300. That's very easy. So what we had to do was mix the convolutional neural net with the recurrent neural net on the source side. So we used the convolutional neural net to detect all those local regularities, and then use aggressive pooling to shorten the length of the sequence quite radically. And on top of that, we use the recurrent neural net in order to get those annotation vectors from the bidirectional recurrent neural net. And then what happens is that because we have shortened the length quite aggressively, it actually works as fast as, or sometimes faster than the existing subword level translation system. And then we tried it on all these language pair directions, and then we noticed that except for German to English, I don't know why, the multilingual character-to-character level was always better. And then in fact, some cases, such as the Finnish to English, it was working substantially better. So why do we want to go for the character level instead of all the other intermediate things, right? So we decided to look at why that is so. And then what we noticed first was that, okay, it's very robust to the spelling mistakes, which is going to be super important for the social media translation or for the conversation translation when the speech recognition system is not perfect. Furthermore, this character level model was able to cope with the very rare words or the really completely novel compounds words very well. So because I don't speak German, I cannot really tell you too much about it, but according to the Jason Lee, who does speak German, this is a completely valid word, compound word, but it doesn't really show up much. And then the BPE-based model kind of, let's say, got confused while the character-to-character level model was perfectly translating it. I hope, is it perfect? No? Wrong? Kind of? All right, I'll pass. Let's just assume that that was really good. Okay. And then you can even see that this character-to-character model is very robust in the sense that it is kind of, let's say, ironic compound, right? So it's going to be the worsening improvement or something, can also be translated really well. In the case of BP to character model or the other models that we tried, what happened with a lot of those ironic compounds is that the network seems to use to just ignore it. I think that's just very rare, and then that was not really expected. And then furthermore, the nice thing about character level is that as we go into the rawer and rawer representation, the commonality across different languages actually grows in terms of the representation. For instance, all the European languages, except for a few, you can always use just alphabets and then write it there. And then the vocabulary is completely shared in that sense. So we decided to train one model that's going to take as the input a sentence, well, as a sequence of characters in any of the 4 languages, and then let it translate it to English. We just trained the model. Of course, there were some tricks that we had to use in terms of how to build a mini batch because the data set size all differ from one language to another, but we could train it pretty well. You can actually read our paper at TACO this year for the detail. And then what we wanted was that by doing so, we wanted the network or the neural translation system to share the knowledge across all those different, let's say, at every level possible, starting from the letters to the sentences. And then we wanted to check whether this model, although the training data did not include any such case, can cope with the intra-sentence code switching. So that is, like if you're a bilingual speaker, then often you notice that you actually mix in 2 languages in a single sentence. And then if you look at the bilingual or trilingual kids, they just do it. They just mix in all those languages into a single sentence even without noticing. Can this neural net do the same thing? Turned out that yes, it does. So if you look here, this is a sentence we made. So that starts with the German, and then it moves on to the Czech, comes back to the German, and then like goes into the Russian, and then comes back to German. So this is a sentence. This is a kind of sentence that never appears in the training set, and then in fact it's difficult to get that kind of training examples. And then this character-to-character model was able to just translate it perfectly. And we didn't even have to tell the model what kind of languages are used, what kind of languages are inside this sentence. What happens is that this network is doing the language identification as well as translation on the fly, and then project the whole thing in whichever language the sentence was written into a continuous vector space. And then from there on, all the decoder needs to do is to simply decode out into English sentence. And then similar thing has been noticed by the Google Translate people as well as folks at the, which group was it? From Germany, I forgot actually. Sorry about that. I'll figure it out. So these three groups actually proposed a similar thing simultaneously, and then they all noticed that you can train a single neural network to do multilingual translation without having to build a specific part for one language, specific part for another language, and so on. And the rumor is that I think the Google Translate might be using single neural net in general for all the language pairs that you use. And then what's some interesting thing about the character level multilingual translation system is that it actually prevents the overfitting for the low resource language pairs. So this is the learning curve on the development set. This is the blue score on the Finnish to English news test 2013 set. And then if we just train a bilingual, so the one language pair direction model, then we see that it immediately overfits because the training set is just so small. But by training together with all the other language pairs where we have more resources, we see that the performance just goes up and up and up and up and up, and then it's difficult to actually observe that it's going to ever overfit. In the sense that the model is so much more constrained that it's difficult to actually make it overfit. So the next lesson or the direction that I see is that, okay, what is the right representation? At which level should we represent the language for the neural nets? In the case of sentence, it seems like the sequence of characters makes sense. But if we go even further into the multimodal sense, and then also the document level translation, what is the right level of granularity that we should, let's say, settle down? I think that's going to be a really important research direction that we need to push forward, especially as we run into more and more low resource languages. And then now the third thing, yes, wait, am I like going not that far in the time? Okay, okay. So the third thing is the decoding. So one thing you learned today earlier in the morning is that the decoding or the finding the translation that's going to have the highest conditional probability given the source sentence with the neural machine translation system is difficult, if not impossible. Exactly doing that is essentially impossible. So then there's a big question of, okay, so if you're going to do any kind of research or the building a product based on the neural machine translation technology, how do we know whether we should improve the model or learning or decoding algorithm? Is it possible that our model is now almost perfect, but we just don't know how to take out the translation? Or is it possible that our model is completely, let's say, suboptimal, and then however better we do the decoding, we won't get the better translation? It's actually impossible to tell at the moment because we don't know how to do the decoding perfectly. So because of that, instead of always pushing on for building a new neural net models or the new activation functions or the new recurrent activation function, which we all learned today this morning that is a kind of pointless thing to do unless you're Google. So one direction that I see is really important is to work on the decoding itself. So I started working on this kind of idea of the trainable decoding. That is, we don't really know what is the decoding objectives during training time. So I got this gigantic translation model I built, but maybe I want to use it for the conversation translation. And then what's important there is not only the quality, but also to minimize the latency. And let's say I want to use this system to translate for the primary school students. If I'm going to feed in the Wall Street Journal news article to this system, what I want is I want to get a very good translation using only the very common words and no, let's say, obscure word there. So we can have a lot of different scenarios for which this neural translation system can be used. And then we cannot really know all those scenarios in advance. And then even if we do, it's difficult to get those training examples. And worse still, so those decoding objectives can be very, very arbitrary. So if I want to put some kind of latency penalty, how am I going to make it differentiable with respect to the parameters of the neural translation system? So what we realized is that of course, there's one way to go. One way is to design or build a new decoding algorithm for every single objective you have, which is kind of very difficult. It's a very difficult thing. And that the number of the objectives will just grow all the way, and then eventually we're going to run into the issue of not being able to build an algorithm for that. So instead, what we decided to do is we're going to train another neural net on top of the existing translation system to do the decoding better. So as an example, one of the examples, we decided to work on the real-time translation inspired by the simultaneous interpretation. That is, we want to not only to maximize the quality of the translation, but also to minimize the delay between the receiving the full source sentence and then generating the translation. So we want our translation system to start generating the translation before the full source sentence was received. And of course, we don't have any data for that. Well, Graham Nubik actually collected some data between the Japanese and English, but that's tiny data, and then we cannot really expect to train or to fit hundreds of millions of parameters of the neural translation system with that data. So what we did was to, okay, we're going to train this model, the underlying translation model, as usual. We just train it with a consecutive translation parallel corpus, and then we fix it. We're going to just fix it as it is. All the parameters are fixed, on top of which we build a neural net-based agent, recurrent neural net agent, that's going to look at what is going on inside the neural translation system, and then trying to figure out whether to wait for the next source word or generate the translation. And of course, one thing is that, okay, so what's the good thing about neural net? Neural net is completely transparent, right? People tell you that the neural nets are black box, they are lying to you. They are lying to you. Because, you know, like, I have this neural net. You give me any complicated input, I can give you, like, at the bit level what goes on inside the neural net. It's like the most transparent machine learning algorithm ever, actually. Kernel SVM is not transparent. You know, like, it's like you project it into infinite dimensional space, you compute the dot product there, and then you get single scalar. You have absolutely no idea what goes on inside that, you know, like the infinite dimensional space. But in this case, we can actually know everything, right? That's actually true, right? I can tell you everything about this. But of course, how to interpret or understand, that's the difficult part. So humans cannot do it. We are not good at interpreting any of the high dimensional vectors. Already at the 3 dimensions, we are completely off, right? So instead, what the idea here is to use a neural net, which is the thing that we know how to that handles the high dimensional vectors very well. We use the neural net to interpret what's going on inside the other, let's say, base neural net, and then trying to make a decision in how to do the decoding better. And then it turned out that it can actually do it very well. So this is the base neural machine translation system. It takes as input a German sentence and then translates it into English sentence. It does a decent job. This is a visualization of the attention weights. You can already see, you know, that it does decent job, especially if you know German. And then we have that system fixed, and then the trainable decoder was trained. And then the decoder makes a decision at every time step whether to wait for the source word or start generating the translation. And then, as I said, there is no such data set where we can get these exact labels. So we just train it with a reinforcement learning algorithm or the policy gradient. And then just after about a few hours, the trainable decoder was able to get this kind of perfect, near perfect, because it can never be perfect, very nice policy to do the real-time translation. And then we got a bit greedier and then decided that, okay, so what's the issue with the neural translation system is that the decoding with the beam search is expensive. So we want to always decode it with the greedy decoding, which we learned in this morning. And then, but we want to do it better. We want our greedy decoder to keep the computational complexity, asymptotic complexity, constant, while we want the quality to go high. So we start with the very same neural machine translation system. We trained it, we fixed it, and then now we build a trainable greedy decoder that's going to first intercept all those internal signals, right? You know, like this one is going to interpret what's going on inside, and then outputs a 1,000-dimensional bias vector and inject it into the decoder. So, you know, like a nice analogy is that this is like how you build a computer virus or the malware. That is, you know, it's going to look at the existing program and how it's going on, and it's going to inject its code in to serve its own purpose. And then what we want is that we want this trainable decoder to inject the signal back into the existing neural net and then modify its behavior. And then we train this whole thing with the deterministic policy gradient. The whole thing is in just this small box to maximize any arbitrary objective. So I won't go into the detail of this, let's say, learning and let's say how the model looks like. You know, you can look at the paper which will be presented at EMNOP in a couple of months. But it's not a trivial thing to train. You have to do a lot of, you know, things. Okay, so you can read the paper. But what you see is that given the very same greedy decoding, If we train the trainable decoder to maximize the blue, it's going to maximize the blue. If we train it to do the maximize the perplexity, it's going to maximize the perplexity, except for finish. That one I'm completely perplexed. But training is still quite unstable without some of the tricks and the variants of the learning algorithm that we propose, and then more work is definitely needed. But what it's telling us is that if you think about what neural net does, neural net, all those layers are essentially all about throwing away the information. That's what machine learning is. That's what supervised learning is. So you start from the image that has, I don't know, millions of pixels. Let's say that was the image of a panda. And then those deep convolutional neural net, what it does is that first it's going to filter out the background. Then next it's going to filter out the whole body. After that, it's going to filter out, like, let's say, how the eyes look like, and then so on, until it gets to a single bit which says that, okay, that's a panda. So it's all about filtering out the information, but in order to filter out the information, what it needs to do is it needs to disentangle the features so that you can tell which features are important, which features are not important, and then you can do the filtering. What it means is that within the neural net, there's an amazing amount of information that has been well disentangled and are thrown away at the end. So if you let another neural net look into the neural net and then see what happens, then you can get actually much more information out of it. So you can do all those, let's say, crazy things on a pre-trained neural net to make it serve your purpose. So let's say, how many minutes do I have? 8 minutes. Okay, so I'll speed it up. Okay. So another direction is that sorry, what? Oh yeah. So okay, yes. So this is about to be rejected from NIPS. The reviews are kind of horrible. I'm writing the rebuttal as well as possible. If the reviewers of our submission are here, please consider that this is a great idea. I think it's worth being accepted. But anyway, okay. So since we started talking about what neural net does and then what machine learning, supervised learning is, if you think about the parametric machine learning paradigm, it's debatable whether the neural net is parametric or non-parametric. It's actually closer to non-parametric because we tend to grow the size of the network as the training set grows. So it's non-parametric, but I'll just assume that we have a fixed number, let's say number of parameters set by the, I don't know, some oracle. So we have a fixed number of parameters. So I'll consider it as a parametric machine learning model. In parametric machine learning model, especially in the supervised learning is essentially a way to do the compression. What do I mean? So we're going to have the training data. We are going to train a neural net using the training set. Once the training is over, we're going to throw away the training data and then use only the neural net. So what the neural net needs to do is to first compress the whole data, and then based on the compressed representation, you need to do the pattern matching. And then data compression part is getting worse and worse as the data set grows over and over. And then the issue here you see is that, okay, training data is used once, thrown away, and then if you have a new training data or the larger training data, what you need to do is you need to train it once more, which is absolutely not the thing you want to do. And then it's connected to the personalization as well as the domain adaptation and all those things. If I could only carry this whole training data over to the inference time, and then if I have more data or the, let's say, stream of data, I'm going to just augment the training data, wouldn't that be great? So that's the idea between this non-parametric neural machine translation system. The idea is we make the neural translation system to use the search engine to retrieve some of the relevant translation pairs from the training set, and then use all the information, including the current input sentence, as well as the retrieved source and target translation pairs when it does the translation. So first, what we do is that we have millions of examples, so the pairs, and then the search engine is going to index all of them according to a source sentence. And then based on that, neural translation system will query the search engine to narrow down into the few hundreds of the relevant translation pairs. And then, we pick only the top case, so there's going to be a very few ones. So we now have the source sentence and the relevant translation pairs. And then this process is extremely efficient. Like the search engines are crazy good. Like the Google is fast, and then like the Microsoft Bing is fast. You can also download the Apache Lucene, which we use here. the indexing is so good that, like this kind of text matching just happens immediately. And then once that's done, what we do is we use the idea from the memory net or the key value memory network. Actually, again, Chris Dyer explained it in this morning, to store all those source target word with a key vector that is extracted based on the source sentence of the specific translation pair. So we have the key, which is the context vectors you get from the attention mechanism, and then the value that corresponds to the target symbol. And then we augment the whole neural translation system with this key value memory, memory. And then we do the matching, get the scores, and then we do the fusion. And still, everything is end-to-end differentiable except for the search engine part. But it's OK to use any generic search engine that has a high recall, because this fusion and the match stages are the ones where the neural net is going to figure out what are the irrelevant things and what are the relevant things. And it's very similar to a larger context neural translation system. Like there were two works, one from the DCU and then one from our group. And then it's quite similar to the neural translation with the external knowledge. So what we see is that, like as the retrieved translation pairs are more and more similar to actual source sentence, we actually get better and better. And then even if they are not similar, we don't really get hurt in the translation. And you can think of it as augmenting the existing neural translation system, because if the matching score is low, you're going to simply back off to the usual translation model, do the translation. But if you see that you have retrieved a lot of similar sentences, you're going to let the neural net only to fuse the information from them to do a better translation. And then what we notice is that we get a higher consistency in style and the lexical choice. So for instance here, so my French is like almost nil. My Finnish is better than my French. So if you look at délai précis, I guess, yes. So that can be translated both as a precise deadline period or the exact deadline. But by looking at this retrieved translation source and the target, the model chooses to use the exact deadline instead of the precise period, which was the phrase selected by the baseline neural translation system, which does not look at the retrieved translation pairs. So I have like 2 minutes. I have about 6 slides. I'll go super fast. So, and then, so that was okay, good, all good, right? But what is the next step? So what is the thing that we don't let our neural translation system have access to is the external knowledge. Translators will have the translation memory, will have the dictionary set next to them. They have access to Google. They have access to everything. Whereas a neural translation system at best has access now to the training set and also its own parameters only. That's kind of, let's say, not a fair game. So how can we make this game much more fair? That is to introduce the external knowledge. So let's think about why it's important to have language in the artificial intelligence or the intelligence in general. So this is an intelligent agent. If it's without language, it perceives the word only via direct sensory information, and also accumulates the experience only individually, because it has absolutely no way to transfer the knowledge to another agent. But by having language, now we can do the collective perception, right? So all of the people here, including myself, we all know that the penguins live in Antarctica. And I'm pretty sure, maybe except for Andy, none of us has been to Antarctica. How do we know the penguins live in Antarctica? Unless you don't believe that, but assuming that we all believe it, because somebody told us, somebody has been there, written down, sent a mail to someone, and then that was, let's say, how the knowledge has been accumulated. And then also we get the historical experience. None of us here has been to ancient Greece, but we all know roughly how the ancient Greeks lived. Of course, taking advantage of these slaves. But anyway, yes, we all know that somehow. And then none of us were there. How do we know that? Because of somebody wrote it down or like told to the next generation over and over. So, and then where do those knowledge get stored? It's like Wikipedia, knowledge base, sometimes Oxford English Dictionary, and so on. And then we all have access. And now I think it's time for us to give neural nets access to those external knowledge. Can we do that? So Seong-Jin An from University of Montreal, who's starting as an assistant professor at Rutgers University soon, proposed recently a model called neural knowledge language model, where what it has is that it's going to look at the previous word, and then let's say previous hidden state from the LSTM, but when it computes the next word distribution, what it does is that it's going to look over the knowledge base and then trying to see if any of the things that has been found to match can be used instead of the fixed vocabulary it has. So they tested with the wiki facts and then especially the actress and actor part, and then they saw that in fact by doing so, the model is able to generate those, let's say, named entities that are associated with the specific actor and actress exactly, rather than just putting out the out of vocabulary tokens everywhere. And then furthermore, even more recently, Dima Badanao, yes, the Badanao of the attention-based model, wrote a paper showing that when you run into a very rare word, it's better not to learn the vectors directly, but to learn to induce that word vector from the dictionary definition. Because we have dictionary. Dictionary tells us what the word is supposed to mean. And then what we can do is we can actually get the knowledge out of the dictionary and then feed it into the neural net instead of just relying on all those word vectors. And then they show that this model can do translation or the other things better, especially when the sentence includes a lot of rare words. And then that's what we do. When we look at a sentence and then when I run into the words that I don't know, I'm not going to simply say, oh, okay, I don't know, right? I'll just pass. Nobody does that, right? We're going to either, of course, these days just Google it or type it in the Spotlight, right? And then it's going to show me the dictionary definition and I can understand. So this is how to build a neural net that can do it on its own. And a few other advances that I think are really important in the neural machine translation and going beyond. Of course, we need to work further on the discourse level machine translation, like the document level machine translation. And then we need to work on the better decoding strategies. A lot of people have started working on it already since a couple of years ago, but it doesn't look like we have the D solution to that yet. We still need to work on it. And then this one, debatable. I'm not even sure if I like it, but anyway, maybe we can do some kind of linguistics guided neural translation. So some of the recent works show that, okay, if you learn to translate and parse together, you can actually do the translation better on a very low resource language pairs. And then, of course, you can do the syntax-aware neural translation. I'm pretty sure Lexi probably mentioned it. And then one of our monitors at the summer school had a very nice paper published earlier this year, showing how to use the graph convolutional neural net with the dependency parse, and then was able to show that it actually improves the performance. And of course, you got to go through the Chris Dyer's lecture slides from this morning. And that's going to be my talk. And then, let's make the neural machine translation even greater. Yes.
Questions?
No, it was too clear, right? Yeah, I know.
Come on, there has to be questions. Yes? No, I speak loud because I think. Yeah.
Oh, yes. Hi.
Is this working? Yeah.
Yep.
Regarding the real-time translation that you were doing, so a lot of language pairs have very different orders.
Yep.
How do you handle that?
That's a great question, right? So for instance, like the Korean, it's a verb final language. And then even in the, let's say, nested sentential phrases, verbs are always at the end. So you got to wait for it. So of course, we didn't give any kind of the knowledge. We just trained a model to maximize the quality while minimizing the delay. So it was just very implicit in the reward. And then if the network figured that, okay, in order to maximize quality, we have to wait while sacrificing the delay, then the network would have learned that. And then in fact, interesting thing is that it doesn't have to wait all the way in order to tell which source word is going to come in. Because how was this neural net trained, the baseline one? It was trained essentially to predict everything. So in fact, when we look at all these hidden vectors within the neural net, there is information about what are going to come later. That's what language model is. So the network can essentially guess what the likely verb is going to be and then start translating. And because of that, we do see some catastrophic mistakes that it makes. But in general, that does help this policy to maximize the quality while minimizing the delay. So there's always a trade-off. But we let the network figure that out. Yes. No questions. I guess everyone wants to go now, right? No?
They can't. So.
Oh no, there is actually. Oh, they can't. Yeah, yeah. Oh yeah, there is a after this, there is a kind of closing remark. So please don't leave. Yes.
You better make question.
Oh, there's a question. Okay.
I got the mic first.
Okay. All right.
So I think you said in your multi-input, multi-output system, where you just had the individual language encoders and the for the input and the output, that the character-based model worked the best. But when you in the real-time translation,
right,
you wait for the next word. Now I know it's a more fine-grained model, but have you tried waiting for the next character rather than the next word?
We haven't done that because of the computational efficiency. Yeah. So the issue is that in order to make the computational efficiency favorable for us in the fully character level model, we had to use the convolution. And then now with the convolution, now it's actually tricky to wait for the next character and then rerun the convolution. So we haven't tried it at the character level, but I think we can be a bit smarter about it, especially now that there has been a lot of work on the fully convolutional neural machine translation system. Yes.
Thank you for the talk. And I have a question about the training data. For Chinese and the English translation, this year in the WMT share task, there are about 24 million sentence pairs. But I also see that in some research papers, they just used about 5 million sentence pair for training. So what do you think about the training data size? So should we use as much as possible, or?
So yes, of course, more data the better. That's actually the clear thing that we see. I mean, of course, the gain we get by increasing the data grows kind of logarithmically rather than linearly. So of course, you're going to see that we have much more data, but the improvement is less than what we thought we would. But even then, what we see is that the issue is that if the data set is small, we see a lot of artifacts. So the improvement you see on a small data set may just be washed out as soon as you have enough data, which means that working with a small data set is actually a great way to write a paper, but I don't think that's the one direction we need to go into. In fact, but of course, that's the case where we have data and then we use only small amount of data. But in many cases, especially in the case of translation and the language research, there are a lot of cases where we just don't have enough data. In that case, now we need to do a lot of, let's say, this linguistics guided approach or the other approaches. But like artificially decreasing the data when the data is available, I highly advise against it.
Okay, because when the data is growing, the training time is also very.
Yeah, I know. But it's like the biology, right? You cannot really advance the whole field by just rushing the growth of the rat when rats are just taking a lot of time to grow. Yeah. That's how I view it. Maybe not a great analogy, but yes, I hope you get the idea. Yeah. Yes.
I found the part about this. You regard this language as just a sequence of tokens, whatever the tokens is, right? I found that part very insightful. So I want to ask whether we can extend this to other tasks like sentiment classification or even retrieval or something. So what do you think about that?
Yeah. So in fact, I worked on the translation for this, but since the early 2016, a lot of other groups such as Microsoft Research on the question answering, and then some other people on the information retrieval, they show that using the character level information as an augmentation often improves the performance. So I think this is a great idea. And then because we don't exactly know at which level we need to work for each of the tasks, what I think should do is actually to let the neural net decide by actually feeding in as much information and then as many different levels of representation as possible.
So you mean feed in the terms and the character in the same time?
Yeah, why not? You can always do that, right?
Hi, thanks for a great talk. So you have all these different ways to improve the neural machine translation, and none of them is really linguistics. Are you leaving that up to others, or do you know something I don't?
Oh, yeah. So that's actually a great question. If you have 2 minutes, I can actually tell you why I take this kind of approach of kind of almost ignoring linguistics is because anyway, all those computational linguists, including Yoav, is going to tell you that, these machine learners need to get inspired from the linguistics and, computational linguistics. But what I say is actually the other way around. I think linguists should actually get inspired from machine learning and deep neural networks. And that's actually a very interesting thing is that I think this is a really interesting figure that I can show you is that this is a paper from the Osling and Tietman from University of Helsinki. So they train a character level recurrent neural net language model with multiple languages, a lot of languages. So they took all the languages where the Bible is available. And then they train a model while giving the language identifier. And then what you get is that for each of the language, you get a vector. And then they did the hierarchical clustering of the Germanic languages, and then you get this kind of tree. And then I was looking at the book, The Germanic Languages by Harvard, and then this is like the tree from that book. And then if you look closely, and then well, at this resolution you cannot, but if you later download my slides, and if you look closely, it's almost perfect match. And then my question is, okay, so these are the Germanic languages, but for other languages, where we don't really have this kind of nice tree of the languages and so on, what can we learn from that? And then furthermore, this is what people used to view translation as, and still some do, right? So this is you analyze and then you generate based on the semantics, syntax, and then word. But now, without all these things, we can actually do the translation. Now, how much can we actually learn from this learned translation with respect to this knowledge? Maybe some of them are wrong according to what we have learned. So I think we should be the other way around, and we, the machine learners, should inspire linguists. That's my view.
Thank you.
Yes. Oh wait, there is a question actually.
In the multilingual, I understood that the other languages training data helps for a language that does not have so much training data. Did you try a scenario where you had no training data at all for a certain language?
We actually did.
Okay.
We actually did. So that's some call it zero-shot translation, some call it zero-resource translation. So for instance, let me actually go to one slide earlier. Let me see, where is it? So okay, let's say I had, So usually the data we have is the data that goes always through English. So we have all the data from English to all the other languages. I have all the data that goes from any of these languages to the English. But I'll probably never have a data that goes from Finnish to French directly, or the Czech. So now the question is, once we train this model, can we do the translation between pair where we didn't have any resource? So the quick answer, no, it doesn't work. But a slightly longer answer is that yes, you can make it work by using a trick of the back translation from the Lexi Birch and then Rico Sandwich that was used for the neural machine translation recently, and then you can use that to generate those pseudo parallel corpus. And then all you need to do is generate few of them and then slightly tune it, and then suddenly the whole model starts doing all those zero resource translation very, very well. So we have a paper from last year's EMNLP on doing that, and then Google's paper by Melvin Johnson also has some mention about that. Yes.
So let's thank the speaker again.
Thank you.